Hello everybody, this is John Barry speaking on the behalf of Joe Mima Construction Group C, and today we'll be talking about our Project 2, Chapter 8, Eccentric Connections, and we'll be going through example 8.9. And as you can see in the middle, I'm holding my prop. This prop is one piece of the connection, one piece of two that we will be solving for today. That connection, the prop to the connection is life-sized. So take a note of the size if you wish. That's what we're going to be solving, and we'll be seeing that very soon. But first, we want to talk about eccentric connections and try to understand that so that we can greater understand our problem. So what is an eccentric connection? Well, it's simply a connection that has eccentricity. So eccentricity is actually a concept that we've been using multiple times, and it is whenever you have a line of action that is a distance away from the centroid of, in this case, a connection. So that's shown by these diagrams, and these diagrams are in Segway 479, which is our steel design textbook. So here we have our eccentricity resembled for E over here, and that shows the perpendicular distance from the point load, the line of action caused by the point load, to the centroid of the connection. That causes us to not only have these forces acting at the direction of the point load, but it also forces it to act in very different orientations, I guess. It causes for these bolts that are going to fill these holes to experience loads at different directions. That's simply the concept of eccentricity, and it's continued up in the top right over here. But this concept of eccentricity, it continues to different types of connectors. You can have here where we have a bolt connection. You can also have shear connections. You can also have weld connections. So you can have multiple connections, but if that concept of eccentricity is held, then we're going to have eccentric connection. And so today we'll be going through a welded eccentric connection. So we have a welded frame beam, which is shown in the figure below, which is connecting a W12 by 72 column, and we'll be using L4 by 3 by 1/2 to be connecting those. As I said before, those are 32 inches long, and the image really does not do justice how long and slender these connectors are. We'll be using A36 steel and A992 steel for the two different shapes. A36 we'll be using for the angles, A992 it will be using for the W shapes. And for the welds, we're going to be using 3/8 inch fillet welds. And so if you look at your top right, you'll see an example, a real-life example of a similar type of connection. It is a welded frame beam connection, yes, but it is a beam-to-beam connection instead of a beam-to-column connection. So it's not a perfect example, but it just gives a little structure and a little bit of real-world example to this problem. And so in this problem, we're going to determine the maximum available beam reactions as limited by the welds at the column flange. So the first thing we want to do is we want to find the moment on the column flange. And to do that, we're going to have to find the eccentricity. So to find the eccentricity, we have to find the center of gravity. And we do all three of those things. Important thing to note is instead of solving the moment and just having a simple value, we're going to be using a variable, which is this r that we're going to be using right here. We're going to be using that. We're going to continue to be using that throughout, so we can find, because we're not trying to see if this passes, so to speak, we're trying to see the maximum reaction that this column can experience. So let's continue. Now we're doing a similar thing. We're finding the center of gravity, this time to the y-axis, and then after that we're going to use that to find the moment of inertia for this connection. So after we solve all the values for the connection, we're going to find different values for the two welds. First, we're going to find the moment of inertia. We're going to find the tensile strengths of the welds. We're going to find the shearing stress and the required stress. And here is a diagram of these welds, these long, little slender rectangles that look put together, look kind of like bendy straws. That is the welds that we're going to be using. Take a note of this required stress. We're going to use that in the next calculation. So as I said, we use the required stress right here, still written the same, and let's go back just so we can see it again. And so what we're saying here is we're going to make this required stress, we're going to equal it out to be one to this on this other side, which we don't know what that is yet. So what that is this 1.392 is a constant, and we use that constant, we combine it with the weld size, and that is going to give us a weld strength. So that constant combined with your weld size is your weld strength. So we're going to equal our required stress with our weld strength. We're going to solve for RU, and from that we're going to get a maximum factored load reaction. And so now we're going to test that maximum factored load reaction through shear yield and shear rupture, and then we're going to compare that to the direct shear that we're going to experience. And so we have our shear yield stress, which is the lesser of the values, and so we're going to compare that to the direct shear resisted by one angle, and we'll get 7.48 kips, which is less than 10.8 kips. And so our factor checks out, and our maximum factor load reaction is 490 kips. And so immediately you might be wondering, I wonder why they rounded up instead of down. Maybe that's a red flag for you. Maybe sirens were going off in your head. And that's what I wondered too. So that's a comment that I'm making for this LRFD method and the person who wrote this textbook. It was very strange of them to do that. So let's move on to the ASD method. So we're going to use that same required stress that we had 2 slides ago. This time we have a different constant factor, but this constant factor that's underlined multiplied by this weld size is still going to give us weld strength. And so we use that to find the maximum service load reaction. We're going to check that with different formulas this time, but they're testing the same thing. They're going to test shear yield stress and shear rupture along with direct shear. And so they found that the direct shear is less than the shear yield stress. And so it's interesting to note, however, that the ASD method, it shows us as having a maximum service load reaction as much less than we had with the LRFD method. But again, we have a rounding up, and this is by a more drastic amount. We rounded up by 0.5 kips this time. Last time we rounded up by 0.1 kips, but still rounding up nonetheless. And so if that's something that makes you uncomfortable, then it's easy as rounding down instead. And so there is example 8.9. So now let's go into our Excel sheet. Here's our Excel sheet. There we are. So as we said before, here's our service load reaction that we just got back from, and our factored load reaction. And if you remember the values, you can see that the values are the same. One way that you can use this Excel sheet I'll go through now, you can change the height of the connection. Now if we were to decrease the height of this connection, it does what we expect it to, and it decreases the factored load reaction of this connection. Another way is we can use goal seek, if I can find it. And let's say we know how much we want we know how much load is going to be set on a connection, right? So we want to set cell, and let's say we have a value of 100 kips, and then we want to change this height of the connection to match that cell. So let's try this. Okay, So we know that the height of the connection needs to be about a 12.5 inches to equal 100 kips. So let's change that to 12.5. Okay, we have exactly 100 kips. It's important to note that the LRFD method returns a larger amount of kips, but just to be on the safe side, the ASD method passes, so 12.5 is the number that I choose. So that's all I have for this project. Thank you guys for watching. If you have any questions, feel free to email me. I'll put my email on the screen. I welcome any comments, concerns that you might have, or any questions about connections. For me, this was really informative, and I was really happy to learn about connections because in our previous classes we haven't learned about anything about them. I also wanted to leave this little joke along as well. But thank you guys for watching. Thank you guys for watching the 3 projects that I've had. Appreciate the feedback and have a good